Welcome everyone. Today we have Brent Lebec from the NVIDIA HPC SDK team. He'll be presenting an introduction to GPU and accelerator architectures. Brent is a compiler engineer and has extensive experience working with NVIDIA and previously with PGI, as having been a co-developer of Cuda Fortran even in the past. Today, he still works with the HPC SDK team and continues to engage in the GPU computing space. So look forward to his talk today, and I'll, if Brent, you go to the next slide, just to cover the logistics of today. Please make sure to mute yourself and turn off your video during the sessions. Questions may be submitted in the chat and will be answered appropriately. You may also raise your hand, unmute, and ask questions during Q&A at the end. And I believe also Brent is okay, perhaps, with some questions during the presentation as relevant. Again, if you're joining today, you're agreeing to abide by UCAR's Code of Conduct. And this recording and other material from this session will be archived and shared publicly later to the workshop participants group. So feel free to follow up with us via Slack. You should have received an invite to that space, or submit support requests to our NCAR support page and support team via support.ucar.edu. Office hours, if you'd like to schedule as such for specific support you might request, that can be scheduled asynchronously through Slack or by reaching out to any of the members of the GPU organization team, such as myself. So next slide. From there, again, you'll read our workshop series logistics. You're welcome to follow along with these slides that are, I'll link in the chat. The main webpage will feature the all the course descriptions of future sessions. There's also a link here for the full, more detailed description and syllabus of the course, as well as other self-directed learning resources that you may peruse in your free time. You should also be receiving access to allocation hours for compute time on Casper. Please only use that for workshop-related jobs or learning type work. Otherwise, please request an allocation. There are startup allocations available for new faculty and early career graduate students. From there, I'll push this on to Brent, and thank you, Brent, again for being here today, and go on ahead.
All right, thanks, Daniel, for the introduction. So just a little background. As Daniel said, I started at PGI about 18 years ago, and I've held a few different positions there. I've always kind of worked in several different areas. And let's see, 9 years ago, PGI was bought by NVIDIA, and they kept the PGI brand for about the first 6 or 7 of those years. And a couple of years ago, we put to rest the old PGI brand, and now we produce or bundle our compilers as part of the NVIDIA HPC SDK. So this is a complete software bundle that is meant to provide developer tools for HPC customers. So kind of at the top level, we've got different programming models and different languages. Fortran, C, C++, and Cuda C. So we bundle NVCC, which is the Cuda, traditional Cuda compiler. And then our own C compiler is now called NVC. Our C++ compiler is NVC++, and the old PG Fortran or PGF90 that people maybe have used is now called NV Fortran. We also include some Cuda libraries called the core libraries. These are mainly for device code and for fast kernels to run on the NVIDIA GPUs. We have math libraries like cuBLAS, which is our implementation of the BLAS, which run on NVIDIA GPUs. cuSparse for sparse solvers. cuSolver is more for dense solvers. FFTs. cuRAN for random number generator. cuTensor is a kind of a high-level tensor library, and we have some interfaces for that, which I'll talk about in a later slide. Recently, NVIDIA bought Mellanox, and so this is kind of still somewhat in process that we are bundling the Mellanox software layers into the HPC SDK, but we have communications libraries, MPI, mainly based on OpenMPI. There's also some NVIDIA specific libraries. NVSHMEM is our version of SHMEM, which runs on GPUs, and Nickel is a collective library. And then for analysis, we have the Nsight profilers. I'm not going to go into those at all today. And for a debugger, we have Cuda GDB, which we provide and have interfaces. So I've been coming to NCAR for several years. I was involved in a couple of hackathons around the 2016, 2017 period, kind of when we kicked off the MPAS port. And so I gave a talk there, and this slide is still a good introductory slide into GPU computing. So on the left, you have a CPU, maybe x86. This one was meant to be a power, like the Power PC in a Summit node. And the CPU is connected to its high capacity memory that you know and love and people have used now for many, many years. The CPU may be connected to an accelerator either through NVLink or through PCI interface. The accelerator on the right, GPU, has many, many more cores than the x86 CPU. Generally has smaller caches than the CPU, especially cache per core, but it has a much higher bandwidth to its GPU memory than the CPU has to its high capacity memory on the left. So the numbers historically have been 5 to 6x more memory bandwidth on a GPU to its memory than a CPU has to its memory, even across all the cores. I don't know what the latest numbers are, but I think the 5 to 6x has held true for quite a while. One thing to note, though, and we'll talk about this over and over again, is that the connection between the CPU and the GPU is usually one of the bottlenecks in the system. So lots of times in our efforts to port codes to the GPU from the CPU, we run into problems where we just are constantly transferring data back and forth between the CPU and GPU. And that will be one of your challenges moving forward as you port codes to the GPU, is how to leave data resident on the accelerator across multiple time steps, across multiple functions, and minimize the amount of traffic across the connection between the left-hand side and the right-hand side of this picture. So there are some other fundamental differences between CPU and GPU, and I'm gonna have about 5 slides here that kind of talk about that. So when I got started in supercomputing, it was about 30 years ago, it was on an IPSC 860, which was a message passing supercomputer, a hypercube, but it was actually even before MPI. It used message passing library called NX. But MPI came soon after. Each node, MPI rank, was basically just a single core. So for your supercomputing parallelism, you use a message passing layer. And at the time, you mainly gained performance improvements via, the semiconductor manufacturing process improvements. And there became, a little bit more ILP, which is instruction level parallelism within the chip. The chip added registers. The clocks were becoming faster and faster with every generation. And as the CPUs became more capable, the software that we ran on those gained a lot of features like dynamic memory allocation, large heaps, large stacks. At this time, Fortran was still using common blocks where we would reuse memory, but as F90 came along, we started to use allocatable memory pointers and some higher level constructs. A little bit after that, Intel introduced the SSE registers. So the diagram on the left was a single core with maybe SSE capability, which was more than one lane to operate on packed data like vector data. So at that point, high level parallelism still was using MPI. We still got great performance improvements with every generation of new CPUs. And vectorization of loops started to become important to take advantage of these SIMD lanes. Now, PGI was one of the first x86 Linux compilers to have, SIMD vectorization capabilities, and that was a major selling point for PGI and a kind of a feather in our cap. Other people resorted to SIMD intrinsics. So at the time that the SIMD registers, SSE registers came out, Intel introduced, intrinsics to use to program with those in case you didn't want to depend on the compiler or couldn't depend on the compiler. From a programmer's point of view, you still coded to the main core or sequencer, the darker blue circle on the left, even though you could have 4 lanes, up to 4 lanes of data being operated on. So there were vector loads, vector stores, and vector operations, but they were still emitted by the main core, or the main lane, I should say, of the process. So then later, around the times of, Opteron, AMD 64, and the follow-ons to that, they started to add multi-core architectures. Some people say this was sort of the beginning of the end of Moore's law. So the clocks were no longer getting faster, but we added more cores onto the CPUs. Higher level parallelism was still usually via MPI, and then there started to become some hybrid codes that used MPI plus OpenMP to split the work across multiple cores on the socket, for instance. NUMA issues began to pop up. I remember at PGI, we always had problems because the pthreads library that was in the Linux kernel was constantly changing. You could never create a static executable because it would never run on different versions of Linux, for example. But that, started to get ironed out as the processors became more and more mature. Another thing that started to happen is as the number of cores increased, the memory bandwidth per core did not keep up with compute speed. And there were lots of studies on this. I helped author a paper with some people from Sandia about this at the same time. As the cores increased, the memory bandwidth per core just started to drop. And the way that the CPU manufacturers dealt with that was to make more and bigger caches for each core. So the L1 cache sizes increased. They added more levels, L2, L3, and all to deal with data locality and the lack of memory bandwidth. So this is closer to where we are today. So a fast, whizzy Intel's new CPU with AVX 512. So everything has expanded a little bit. This is an example of maybe 8 lanes of double precision, down the columns of AVX 512, and maybe 32 core chip. AVX 512 hardware has been a little slow to take hold. The initial implementations were not optimal. I think they're getting better. We went through a big phase in our compiler group where we would target AVX 512, and if we ran more than one core on the chip, things would just run slower. And so a lot of compilers just defaulted to AVX 256. The NUMA issues continue to, be a problem. They seem to be different on the AMD chips than they are on the Intel chips, and it kind of depends on the family. Vectorizing compilers are still very important on AVX. SIMD intrinsics are still in use. People have, ported their 128-bit SIMD intrinsics to 256 bits and then ported them to 512 bits. And we see it in a lot of, open source codes out there that they have the bandwidth and the people to continue to move forward with the generations. Memory bandwidth continues to not keep up with compute speed. More and bigger caches. Software still grows in complexity. The features like dynamic memory allocation, larger heaps, large call data stacks. One point, you still code to the main core sequencer. So you still kind of code it as a single lane, like the darker blue on top, but they still have a model of large vector loads. So a load that loads 512 bits at a time. All right, so now we're going to compare and contrast that with a GPU. So this is a representation, actually an underrepresentation of an Ampere A100. So a GPU is broken up into at least two dimensions and two important dimensions. So the columns in this diagram represent a symmetric multiprocessor or an SM. And the across the columns represents the number of SMs on a GPU. So an A100 has, I don't know, 102 or 108 something SMs. The numbers are a little fuzzy. Within a column, down a column, 32 dots here make up what they call a warp. And a warp of cores basically run almost as what you would think of as an SSE lane, an AVX lane. This is actually underrepresented in that in a single instruction on an A100, you can have 64 threads, so double, the height of this diagram, number of cores running every cycle. An important point on a GPU is that between columns of this diagram, so between SMs, symmetric multiprocessors, synchronization is very difficult. And the typical Cuda model is that there is no synchronization between columns in this diagram until the kernel that is running ends. Now, we'll talk a little bit more about that, but that's kind of a general rule. So your problem that you will face as you move to an A100, and this is, to me, over the years, this is the biggest problem people face. They don't understand the level of parallelism that is available in a GPU. So if you take, the latest, nicest Intel CPU with AVX 512 and stick it on the A100 diagram, it takes up maybe 1/12, maybe 1/24 of the number of cores that are available on an A100. So if you have trouble filling up all the cores on your Intel chip, you're going to really struggle to fill up all the cores on an A100. And we'll talk about this a little bit more in this next slide. So this is kind of the summary of the differences. So on an Ampere, we still use high-level parallelism via MPI. And some applications actually do use OpenMP and have multiple OpenMP threads talk to multiple GPUs. The GPU is so large that some applications have to break up the work. And there are several ways, and I don't have time to go into those today, but you'll hear things about multiple CUDA contexts, CUDA streams. MIG allows multiple jobs to run on a single GPU. MPS is another way to allow sharing of the GPU resource among multiple ranks of an MPI program, for instance. As I said, synchronization between the columns in the diagram is hard. It's not, I used to say impossible, but it's not impossible. There's been a lot of clever people that have found ways to synchronize between the columns. It usually involves atomics and some setup code, and it's mainly only accessible through coding in CUDA. The programming models, higher level programming models, don't really allow that. More than vectorizing compilers, offloading compilers are important. It's important to be flexible in the way that the language presents kernel scheduling, the launch parameters, and synchronous or asynchronous behavior of the kernel launch. Again, memory bandwidth is many times higher than a CPU, but the memory latency for a single thread to access the GPU memory is very high. And the caches on a GPU are relatively small. There is a programmer managed shared memory cache, and will show an example of using that. And that's useful for performance. That is mainly used from the CUDA level. It is exposed a little bit at OpenACC, and we'll talk about it. But the key, one of the keys to good performance on a GPU is massively oversubscribing the core. So for instance, if we have on an A100, I'm just going to throw out a number because I don't know exactly what it is, 7,000 cores, maybe 6,500 cores, hardware cores, you want 10 to 20 or higher times as many threads running on those cores in any kernel for best performance. So that means you want to launch 10,000 threads, 20,000 threads to run on those 6,000 cores. And the reason for that is when you oversubscribe the GPU cores, they have a very fast capability to context switch. So a core will do a memory read operation, for instance, and as it stalls on the very next cycle or within 1 or 2 cycles, another core can take over execution and make progress, up until the point where it reaches a stall. So in finally, well-tuned GPU codes, almost always they way oversubscribe the cores so that they can hide the memory latency and take advantage of the high memory bandwidth. So we'll get into that, and it's a very important consideration. The programming model is actually a little different. So if you have any CUDA experience, you actually code to the core and lane. So this is different than, I kept kind of mentioning on a CPU, even with AVX 512, you still kind of just code to lane 0, and the main control unit does vector loads and vector stores. So that's not really how the GPU works. You code to an individual dot anywhere on the diagram. So it's up to the OS running on the GPU and the low-level runtime that handles divergence within the warp, or takes a set of 32 reads from each of the 32 threads and kind of coalesces that into one big wide memory operation from the GPU. So you'll hear a little bit about warp divergence and warp convergence as you gain experience running on the GPU. And that's what that means, is that I can put weird conditionals in my Cuda code that says if I'm thread number 27, do something different than all the other threads. And that's just fine. But there will, the GPU runtime will handle that for you at some cost. Finally, each core and lane has a small stack, a limited number of registers, and relatively limited number of system options compared to a CPU. So to think that code that you have that runs with OpenMP and at a high level you launch 4 threads and then each thread kind of runs through your whole program, that just does not generally port well to a GPU. You'll run out of registers, you'll run out of stack, and just think about the work as it's distributed across all these cores. So going back, let me just go back one slide here. If I had a matrix and my matrix was 64 by 100, every core in this diagram would only operate on one element. Now, if it could operate on one element very quickly, the operation will be done in just an instant. As long as it takes to launch the kernel and do, the operation on one circle in this diagram, you're done. Unfortunately, the way codes have been, structured recently for CPUs, because CPUs are so capable, there's overhead. There may be function calls, there may be dynamic memory allocation, and on the CPU, a lot of that overhead is amortized because the CPU thread does many iterations, a high percentage of the matrix, maybe 1/4 of it if it's spread across 4 threads. On a GPU, each thread does 1 element's worth, 4 small, problems. So a lot of code porting that is done to a GPU is pulling out a lot of that overhead that is just redundant for every thread to do a whole bunch of work just to compute, 1 element. So that is, again, one of the major problems that people have to address when they move to GPU. So there are some general recommendations that are in the GPU tuning guide, Cuda best practices, and I want to just talk through ways quickly and what that means for you guys. Find ways to parallelize sequential code. Of course, it's Amdahl's law, and sequential code will limit, the speed up you get running in parallel. There are a lot of algorithms used, even that I've seen in weather and climate codes, that do have parallel implementations. For instance, a tri-diagonal solver. There are ways to parallelize that, even though lots of times it's written just as a forward sweep and a backwards pass to do the tri-diagonal solve. Things like I'm currently working on pack intrinsic. So in Fortran, it's one of the F90 intrinsics to pack an array. So the usual implementation you can think of as serial, because you don't know for sure how many elements are going to pass the mask test to pack. But there are parallel implementations of that too. So look for parallel algorithms for your sequential portions of your code. Of course, minimize data transfers between host and device. So that was the small little, NVLink or PCI connection. Just kernel launch configuration, more of a minor one. Ensure global memory accesses are coalesced. So this can result in huge performance gains on the GPU. And basically what this means is if I have 32 threads working together in, as we call that, a warp, I will get many times better memory performance if each of those threads are reading sequential data from memory. If they are reading down the column in Fortran rather than across the row in Fortran. Minimize redundant accesses and avoid long sequences of diverged execution by threads within the same warp. Small sequences can just pretty much be handled. You don't really see too much of a performance hit. If you have huge sections of conditionals to handle different cases of your application, that may be a problem. You may end up wanting to have just multiple versions of the kernel. A lot of times, the condition is set, based on the input parameters, not on any runtime condition that changes. So that was kind of how we got to here. Now I'm going to spend the rest of the talk talking about what we provide to get you to where you want to be, which is running efficiently on a GPU. So we basically think about 3 different levels of coding for the GPU, and we have all 3 of these levels in Fortran. So I know not all of you use Fortran, but a lot of you do. So I'm going to mainly talk about Fortran. On the left, we are starting to work pretty hard on standard language parallelism. And what that means in Fortran is mainly, but not only, do concurrent. So the middle box here. So, and we'll talk more about that, but that's a standard Fortran do loop that says all of these iterations of the do concurrent can run in parallel, or that's the way that we're interpreting do concurrent. The Fortran wording is not exactly that, but that's the way we're interpreting. In the middle is OpenACC and OpenMP. So these are directive-based models. You've probably heard a lot about these. OpenACC we've been working on for over 10 years. Even before that, we had a PGI Accelerator model. And then OpenMP, we have been working on for the last few years, and it was part of a delivery to NERSC as part of the Perlmutter, the big new Perlmutter system. And that is, I think we have met all of the milestones for that delivery. And so I guess we could say our OpenMP implementation for target offload is mature. And then on the right, this is kind of one area I've been very highly involved with is Cuda Fortran. And this looks like Cuda C, but in Fortran. And I have a few examples of that, but this gives you very low level access to the Cuda, NVIDIA GPU hardware and software features. And it's very explicit. You basically have complete control, but all the work to do as well. Then, of course, there are the acceleration libraries that we talked about on one of the early slides. The Fortran do concurrent is standard Fortran. The syntax of it is included there. There are some extensions that maybe you're not aware of. Locality spec. So this is similar to OpenMP's like private or shared. basically saying the variables that are inside the loop, do we need a private copy of them or a shared copy? You enable standard par offload to GPUs with our compiler using the -std par over here on the right. Without that, we will, still accept the do concurrent syntax, but we will not offload that onto the GPU. So there is a code, maybe some of you know about, written by Matt Norman at Oak Ridge, who's been involved with a lot of hackathons that I've been to, and called Miniweather. And there is a port of Miniweather to do concurrent, and it runs actually very well. So just the second line down on the left-hand side is the do concurrent statement. You'll see the loop extents 1 to nz, 1 to nx plus 1, declares some of the variables local, and it basically just works the way a do loop would do, but it offloads it to the GPU. So if you've used our compiler before, we really recommend that when you're offloading to GPUs, you use our minfo flag, which gives you some output for the loops that we offload to the GPU. So here minfo tells you at line 253, which is the do concurrent line, we've parallelized that across CUDA thread blocks, 32 threads, 4 threads, block index, thread index for the 2-dimensional K and I. The inner loops here, the do LL and do S, run sequentially. So every thread runs those loops. It turns out in this benchmark, that's the right thing to do. Those loops are small, like size 1 to 4. Another spot in Miniweather has some reductions in it. And so our compiler supports the reduce clause, starting with our 21.11, which was our November of 2021 release. So a lot of times our compiler can detect reductions by just implicitly. As part of our analysis, we see that there's a reduction. But you can actually specify that, and that is typically more correct. There's a reduce clause in OpenMP and also OpenACC, which is almost the exact same syntax. So here we will, in our minfo message, we say we're generating a reduction. We have some current limitations in do concurrent. This is work in progress. Do concurrent in Fortran requires all function and subroutine calls to be pure. So if you just take a do loop that has function calls in it and convert it to a do concurrent, you may run into this. And we're not quite sure what we're going to do about that. Maybe we will, under a flag, relax the requirement that all subroutine calls be pure. Otherwise, as a programmer, it's your responsibility to say, yes, this is pure, and just put the pure attribute on those function and subroutine calls. We follow OpenACC and OpenMP defaults for scalars. So scalars are first private local, and arrays are shared by default. Not sure. I have trouble reading the Fortran spec to know whether that is in line with the Fortran spec or not. In fact, standard par currently enables OpenACC. It's built on top of OpenACC. So we share a lot of the runtime and analysis in our compiler across all the models. Do concurrent lacks some control over GPU scheduling, which we have found useful, like forcing a loop sequential inside a region. So OpenACC, you can force, actually in OpenMP as well, you can force an inner loop not to run in parallel, but to actually run sequentially by all the threads. There's no control equivalent to OpenACC's gang worker vector, Cuda Fortran's grid and block launch configurations. You know, those things were added because they're useful, not like we just wanted to add things. So we're kind of trying to figure out a syntax maybe that we can add to do concurrent to provide that for users who are interested in, you know, using a specific launch configuration. And there are other things in Cuda that we don't really support. Down below, no control over the stream, which is offloaded. So Cuda has this notion of parallel streams that can be running. So that cannot be expressed with a do concurrent. It's not as interoperable yet. Again, we try to have all three levels of standard parallelization directives in Cuda Fortran be able to interoperate with each other. We have a little bit of a problem there. Standard PAR option enables automatic use of managed memory. So if you don't know what managed memory is, I'm going to go through that really quickly here. So this is a Cuda C example, but you should get an idea for it. So what we do with managed memory is there's a Cuda call called Cuda malloc managed. And that is similar to a Cuda malloc call, except for the data can be managed by the driver and migrate. Think of it as almost like how virtual memory works on a CPU. So you call Cuda malloc managed, it creates some space. I call memset on the CPU, and it, you know, fills the array with 0 or something on the CPU. And so so the array is currently residing on the CPU. I call a Cuda function here called setValue. I jump over here. When I actually do the store into that Cuda malloc managed space, it will page fault, and the page containing those addresses will actually move over to the GPU, just like virtual memory. So this enables a lot of nice high-level programming features. So for instance, in OpenACC, if you use unified memory that can page back and forth, and you compile with the GPU equals managed option, C malloc, C++ new, and Fortran allocate are all mapped to Cuda unified memory. And so basically under the hood, we call Cuda malloc managed for allocation of all of that dynamic memory. So in general, you no longer need data directives or to worry about, is this data in host memory or is it in device? So this is a nice feature. It makes early porting much, much easier. You know, over the years, we've really come to understand that generating the kernel from the compiler is really the simple part. Managing the memory is where all the work is. And some of that work is just on the developer. And some of it, we, you know, as part of the compiler, we try to make it as easy as possible. But that's, you know, if you talk to anybody that's been porting big codes to the GPU, you'll find that most of them say, you know, managing the data is a lot more work than just getting the kernel to be tuned and run well. So these options use are standard parallel options. Both Fortran and C++ assume managed memory. So here's another example where we can take standard language calls, in this case, random number and matmul, and these actually sit on top of a tuned library called cuTensor. So I mentioned before that in our HPC SDK, we have a library called cuTensor and curand. So random number will actually call into our curand library, and matmul will actually call into our cuTensor library. And you can see, you know, matmul, for instance, will run hundreds, maybe 1,000 times faster than the hand-coded matmul on the left. Of course, matmul is what NVIDIA AI lives on. So there are a lot of engineers who work on making matmul run as fast as possible on NVIDIA GPUs. So if you have a code that makes a lot of use of matmul or matrix multiply of any form, you'll probably get good results on an NVIDIA GPU. It's not just matmul, but the cuTensor library can take any type of general tensor operations. And in Fortran, that maps to matmul, reshape, and spread. And cuTensor also takes the ability to scale the operands to those operations. Transpose is a special case of reshape. So transpose is included in this. I wrote a blog article about this, and it's down there at the bottom. We also work in Fortran to provide other interfaces to libraries like LAPACK and BLAS, and just do the work for you, so you don't have to call the Cuda libraries yourself. So on the left is like the zgetrf is the standard LAPACK LU factorization call. And if you run that on a CPU using our LAPACK and BLAS libraries, you get about almost 500 gigaflops. If you ported that to cuSolver and run this on a GPU, these are the types of calls you have to do. You have to get a handle, you have to figure out the buffer size that's needed, then you call the cuSolver routine, you deallocate the work buffer. And really, it's worth it because you're getting, over 3,000 gigaflops or 3 teraflops there. But it'd be nice if for every LAPACK call, you didn't have to do that. So we have that in a library called NVLA-math. So this is, again, standard. It's not the standard language, but it's the standard library call. So if you link in NVLA-math, and again, here's our GPU equals managed option. It runs basically the same speed as if you did it yourself. And basically under the hood, that's what we're doing, is the instruction sequence in this sense. So we have that for a few, I should say more than a few, about 30 or 40 commonly used LAPACK calls, and for all the BLAS calls, you can do that as well.
Brett, just a reminder, there's about 10 minutes left, so just keep that in mind for the rest of your slides.
Okay, yeah, I'm going to go pretty fast through the next part. I wanted to spend more time on standard language and less time on the other. So there's some possible future work, more work on do concurrent to add non-standard capabilities. We have more F90 intrinsic support coming along. I'm working on pack, as I mentioned, merge, operations like that will run fast on a GPU. We'll add more routines to NVLA-math and continue to take advantage of hardware and software. So quickly, the center block in our ways to program GPUs is OpenMP and OpenACC. I just wanted to give some quick examples of how to use those. I'm sure you'll go into much more detail in future sessions on that. So for compute constructs, it's OpenMP target teams, and there are 2 basic forms of that. We're recommending you use loop, OpenMP target teams loop, which is the upper left. You can also use, this is the more traditional form, OpenMP target teams distribute, which is the center example on the left, and then internally do an OpenMP parallel do. So in our compiler, teams distribute will parallelize across the SMs or across the thread blocks, and OMP parallel do will parallelize within a thread block or like down one column across, the threads in a block or a warp. You may see code like the lower left. So this is more for a CPU with AVX or SSE, where it uses OMP SIMD reduction. So our compiler and a few other compilers which target GPUs do not parallelize based on OpenMP SIMD. We ignore SIMD. So just be aware of that, that different compilers interpret SIMD differently. On the right, OpenACC has basically two forms. One is ACC kernels loop, which says, offload the next loop into a kernel, and a little bit more explicit form, which is OpenACC parallel loop gang vector, which gives you a little bit more control over how it's mapped to the GPU. Data directives in OpenACC and OpenMP are almost identical. So we use the exact same runtime for each. We interpret, each of them and basically end up in the same spot. So I've listed each of those here. There's directives for, creating data, copying it in, copying it out. In the name of time, I'm not going to go into too much detail. Just know that they are basically identical. In fact, you could write an entire application using OpenMP data directives and OpenACC kernels, and it would just work great. And in fact, there are applications that mix the two in the same program, finished application. It all kind of comes down to a difference in philosophy in the compilers. I'm not going to get into this too much. There's prescriptive, which is what most people feel OpenMP is, where you're really prescribing how the compiler should parallelize the code. And there's little or no analysis by the compiler. A lot of OpenMP runtimes are just handled kind of in the front end, almost like with at the point of doing macro preprocessing. Descriptive is gives the compiler a little more freedom, and you're basically just telling the compiler, look, the iterations of this loop can all run in parallel. You could run them forwards, backwards, in any order. They're independent. So it's up to the compiler to do the right thing. So it's sort of a matter of trust in your compiler, but it's maybe at a level that some people just aren't that worried about. In either OpenACC or OpenMP, it's important to know how to pass device pointers into libraries. So of course, in both models, you can do that. So this makes all the Cuda libraries accessible from higher level directives. You want to call subroutines or functions within your kernels. On the left, OpenACC is a little bit more explicit about the level of parallelism that you're at. There's routine gang, and it can call a routine vector. A routine vector can call a routine sequential. You move up on the left. OpenMP, you basically just say OMP declare target for any function or subroutine that is called. It's a little bit more up to the compiler to do the analysis to figure it out, or to generate kernel code or subroutine code for device functions that can handle different configurations. We basically don't have a lot of experience with this yet. You can see that we had an error in 21.11, and this just got fixed in our last versions of our OpenMP compiler. So I don't have a lot of experience to share with you. Fortran array syntax in device code. So we don't support that really at all in OpenMP. And so if you use a lot of Fortran array syntax, you're kind of stuck with doing what we have on the left, which is using ACC kernels around an array syntax. assignment operation. Asynchronous behavior, this is kind of an advanced topic. I'm not going to go into too much detail, but it is possible in both models, OpenACC and OpenMP, to take advantage of, which underneath the hood is Cuda Streams. So this allows you to, have multiple streams of execution or queues in OpenACC kind of in flight at any time. Using shared memory, I'm just going to skip over this. It's useful for performance reasons, and we do expose a little bit of that in OpenACC using the cache directive, which is 4 lines down on the right-hand side. We don't have anything equivalent to that in OpenMP yet. One last look on the far right of what we provide is Cuda and Fortran. So there's some extensions like the device attribute and the chevron syntax for launching kernels. You can see that you still use normal Fortran for allocating data. You can use assignment statements for actually moving host data to the device. You can call special subroutines called global subroutines that are, the entry point for the device kernel. There's some attributes for shared memory, built-ins for determining my thread number and block number. And this is where I said in Cuda, you code to the, the actual core or the actual thread. It's because of these built-ins. So I can do decisions based on my thread number and block number and things. There's synchronization. I'm not going to go into that anymore. Finally, this is my last slide. Even in Cuda Fortran, there's ways to write portable Cuda Fortran. So we have the Sentinel, which is only recognized if you turn on Cuda Fortran programming, which is bang at CUF. So anything that is specific to Cuda Fortran, like bang at cuff attributes managed, to say that A, B, and C are to be allocated using Cuda malloc managed, can only, will not affect your code if you don't compile for Cuda Fortran. And we have a way to offload just do loops in Cuda Fortran that operate on device or managed data called cuff kernels, where you explicitly give the Cuda launch configuration in Chevron. So that is it. Sorry, I took all hour, didn't leave much time for questions, but those are the offerings that we have as part of the NV HPC SDK, different levels for programming the GPU and how to access libraries and interoperate between those. Thanks.
Thanks, Brent. We have a few questions in the chat, which I'll go over. Let's start with Gion's question. What is the motivation to transfer from ACC parallel / kernel to do concurrent?
So the motivation would be do concurrent is standard language. So any Fortran compiler should be able to do something with do concurrent, meaning parallelize it across CPU cores. At some point, our efforts on F18, which is an open source kind of version of Flang compared to Clang, will be out in the real world, and so anybody can, target other GPUs or any type of architecture using do concurrent, and not just with our compiler. And so it will be standard language, not part of a directive-based model.
Thanks. So we have a next question from Gus. We have, Standardization of Fortran, C, MPI, OpenMP, for example, have standards and governing bodies, etc. What, if any, is the status of the GPU software standardization?
So OpenACC has a standardized body. And OpenMP, does, and, all the target offload is part of the OpenMP standardization. Cuda is a proprietary programming model from NVIDIA. So there is no standards body for Cuda. And then Fortran's do concurrent, and C++ standard par is part of the language standardization efforts. Did that answer the question?
I believe so. I mean, they can respond in the chat or unmute themselves. They also have a follow-up question of there's a long history of bickering between Intel and AMD about compiler compatibility and the use of SIMD instructions. Is the NVIDIA compiler universal in the sense that it exploits the best of SIMD instructions regardless of the CPU manufacturer?
So we try. So by SIMD instructions, I hope you don't mean SIMD intrinsics, like the intrinsics that, map one-to-one to a SIMD instruction. Our vectorizing compiler, we try as hard as we can and have manpower to match Intel's performance by their vectorizing compiler to map to SIMD, like AVX instructions, SSE instructions. Obviously, our team cannot be as big as Intel's for targeting Intel architecture, but there's real people working on that every day. I can say that. We also target PowerPC for like Summit and the Lawrence Livermore machine, and we're targeting ARM. Our compiler, like a lot of compilers now, are front ends over LLVM back ends. So we get to leverage a lot of the community effort to, generate good code for the CPUs from the LLVM group.
Thanks, Brett. I don't know if Gus wants to comment on that further, but nonetheless, one final question from earlier in the session, a little bit of an aside, but does PGI Fortran and/or I imagine they might be referring to NVHPC SDK compilers work on Jetson Nanos yet?
So I guess I don't know the answer to that. I mean, I know what the answer is, but I don't know what the official answer is. When ARM when we first started targeting ARM, Jetson was the only machine we had access to. So all of our QA ran on Jetson. Now Jetson is like has it been, that's not the group that I'm a part of. So I'm not even sure. I think they've moved on to a new hardware, a more capable ARM processor. So the practical answer is yes, our ARM compiler runs on most ARM processors, but that may not be the marketing or product manager answer. So I'm not sure exactly what the right answer is.
That's okay. Perhaps we can follow up later offline on that particular question.
Okay.
Gus did have a follow-up, assuming you have time. We're 5 minutes over, but feel free to leave as you might need to. You see, did you? Okay. You seem to imply that in the GPU, there's an extremely high level of granularity, which requires extreme discipline in programming. The examples all show usage of, well-organized memory, through rows and columns, linear algebra, FFTs, etc. Is there a more general outlook and possibilities for? Might need to clarify that. Is there more general outlook and possibilities in that space targeting the granularity they're referencing?
I guess I'm not sure I completely understand the question, but you can write anything you want in the kernels. It doesn't need to access memory sequentially or in any type of fixed form, or you can have pretty much random memory accesses. Your performance may not be great, but the GPU is very flexible. You can map the threads to different pieces of work. People have played around with like data flow, type operations. I mean, it is completely programmable. I think problems you will run into is that you may have problems with those type of specialized problem types filling a GPU. Meaning, the blocks of work that you have to do are in the 10s to 20s, not in the 10,000s to 20,000s, right? And so that's why a kind of a straight data decomposition method usually works best on a GPU.
There are a few more questions, but considering over time, I think I'm going to encourage follow up on that maybe offline. Nonetheless, thank you for your time, Brent, and we appreciate you giving this presentation for our group. Any other comments you would like to make?
No, thanks for hosting me, and I will join your Slack and try to answer questions best I can.
Yeah, we appreciate that, your ability to offer support to everyone in NCAR, especially as we're preparing for the RAID show in the future. GPU cluster would appreciate any support you can offer. And of course, again, thanks again everyone for joining today. We'll have later sessions. Next session will be on software infrastructure and make systems. So feel free to stay tuned for next topics. Otherwise, stay involved in the Slack channel and reach out to us workshop organizers for any additional information or support you might need in your GPU computing journey. Thanks again, and have a great rest of your day.